tarde, pessoal, de volta do almoço. Vamos continuar aqui as palestras dos professores convidados. N. Boyer, Azim Rossanali, continuando o que foi abordado pela manhã, certo? Agora à tarde um pouco mais de profundidade nos assuntos. O assunto da manhã foi mais um background do que virá agora à tarde. Pela manhã foi uma introdução à Data Intelligence e também Data Mining and Knowledge Discovery. Agora à tarde a gente vai ter 3 tópicos, certo? A Case Study, Educational Data Mining, Social Recommender Systems e Social Network Analysis, certo? Eles vão começar as apresentações e a gente depois vai abrir para perguntas, certo?
Thank you. So just now to start this afternoon, I will show you some case studies of what has been said during the morning session. So the first one is a case study about educational data mining, and I will show you 3 different projects in which we are involved around education. So the first one is named Back Analytics. It's a back. So if you remember this morning, Azim shows you this graph. So I will use it and illustrate it with the 3 different projects I will present you. So the first one is back analytics, and back analytics, the first step in this graph is to have a business understanding. So first of all, I will try to explain you what is the aim of the project, and then after that, how we proceed in order to mine the data we have. Back is a degree at the end of secondary school. It's the first diploma you can have, and which is required to enter at the university. And then in order to have, it's a national exam, and in order to have it, you have a two steps process. The first step is a set of exams, so you have a 10, 11, 12, depending on the profile of the back you want to have, different disciplines, and then you have exams. And after that, there is 2 thresholds. One is so you have 3 possibilities. Either you are successful, it's okay for you, it's finished. Either you are under a threshold, it's also finished for you, but you failed. And there is a third case. You are between the case of success and failure, and then you can never take exam. So at this moment, you have a second set of exam. And the principle is the following. The candidate selects 2 disciplines for oral examinations. He did that at the morning at 8 o'clock, and just after that, he will pass the exam. It's oral exam. So we have to have a lot of teachers waiting for students selecting the discipline of the teachers. And the question, as it is at the national level, we have 1,000 and thousands of students at this second step, how to minimize the number of teachers. Because at the moment, the organization of the back requires to have a lot of teachers, and many of them have no students, because no students select the disciplines. So the idea is the following. Each year, all the results of the back are stored, because it's a national exam. We have to keep that at least 10 years. And we assume that a regularity exists in the selection of the oral exams by students. So we plan to design the user model for the current year based on the choice that the students made the previous years, in order to predict what disciplines the students will select. So it's a principle of, and the topic and the aim is to minimize the number of teachers we need to have. Just let you know that almost 50% of the teachers have nothing to do. But they need to be there, they are paid to be there, and they have to wait for the whole day, something very boring. So the second step of the process is data understanding. What kind of data do we have? We have the results of the first group of disciplines. So for each candidate and for each exam, we have the result he has. It's something like a grade. And after that, we have a second kind of data, the rules of the bac, because we have different kinds of profile for the bac. You can have a vocational bac, you can have a bac in humanities, you can have a bac in maths, in physics, and so on. So you have specific rules for each profile. So we know the rule because there are constraints on the selection dependent of the back profile. Just let me say that the rules of the CAT can change every year just to have the adaptation. And you can select 2 disciplines when you are a candidate among the long list, and you can have sometimes 50, 60 different disciplines, and you have to select 2 of them. So the third step is the data modeling. Data modeling is now to build, to design a model based on this data, able to predict how many teachers to have. So the question we have to answer is a question of prediction. So if you remember the Gartner figure of this morning, the question is the third one: how can we predict how many teachers we need? And we have a 4 steps process. The first step is that we made an hypothesis. We say that we can predict, we have within the data the sufficient knowledge in order to predict what the disciplines the candidates will select. So we have to confirm this hypothesis, because if it is not true, it's nothing to do, we can't predict anything. So the first step is a feasibility study. Is it possible to predict the 2 choices of a candidate only knowing his result as a first step? The second step of the process is a performance study. If the assumption is true, then we can do a prediction, a modeling and a prediction of the selection, but we have to find the right algorithm in order to do that. And we have to find the algorithm able to run with the data we have, able to predict the results, and with the highest performances, the highest accuracy as possible. The third step is the prototyping of the application. Then when we have to prove that the algorithms that we have designed runs really and is able to predict really what will happen. So we have last phases, which is the evaluation in real situation, what we did just before coming here last week. So the first step is a feasibility study. Just remember, we just want to know if the assumption which is at the basis of the model is okay or not. So is it possible to predict the choices of the candidates only using machine learning techniques without any other information, any other support from any expert or nothing like that? So the data we have as a result of the edition of the 5 previous years for students who have to pass the second step of the bac. And we have the rules of the constraint of each bac profile. To experiment that, we decide to use different kinds of algorithms. And you know there are for mining data a very big set of possible algorithms. So we decide to test some of them because it seems to us that they adapt to our data and to our objectives. So we try neural networks, very basic one, not deep learning, because to do deep learning we need supervised learning, and then we need to do supervision. We have decision tree, we have random forest, we have 6 or 7 different kinds of algorithms, and we run them on the data we have, and the objective is to see for the last year is only knowing the results of the first step, we can predict the selection of the 2 disciplines the candidates wants to have. Here you have the results for 3 of the different algorithms that we have. The first one in neuronal decision tree, and third one random forest, but we have all the results for all the possible algorithms. And then you can see if we want if we measure, if we are able to predict at least one good answer, one good prediction, we have able 98% of accuracy of good answer. So we are able to predict at least one good answer among 2. And if we want to know if we have a prediction for the two disciplines, two selections, then you can see that the accuracy decrease, and we are about 60%. But what we want to know if we have teachers, if the number of teachers we has to be there is correct or not correct. It's what we call the couverture, the coverage, it's a coverage measure, and you can see that we are okay with an accuracy of 90%. So it's relatively high, it's perhaps not sufficient, but it's relatively high. So we can say now that the assumption we made is correct. We are able to predict with a high accuracy the selection of the two disciplines. It's okay? Then now, as the assumption is clear, we can work on more deeply on the real questions that we have. How many teachers do we need to have? At the moment, we just check the hypothesis, the assumption. But now we want to optimize the number of teachers, so we change the problem, and now we want to know that using one of the algorithms we had tested before. So we need to add some constraints linked to the real organization of the bac at the national level. And for example, a teacher, we need to know how many exams he can have in a day, within a day. If it's depending on the discipline, it can be 2, 3, 10 students that can have the same teacher the same day. So we had these constraints, and we want to have a new factor for evaluation. What is important here is now to determine how we can assess the performance of our algorithm in the specific context we are. You know, there are a lot of accuracy measures and so on related to data mining, but it's only to have an idea of the performance of the algorithm without any specific application and any specific application. But when you have a real application, you have to determine what are the criteria of success for you. So the step now is to say what is for us high performances. And then we defined a new score of which is called the percentage of redundancy. So we need to have enough teachers. So we had better to have a little bit more teachers than really required, and not take the risk of a teacher missing for a specific disciplines. So we want to be with a performance of 100%, and we accept a redundancy, some teacher coming even if there is no exams, you know? Just, I want to give you an example. It's possible to have math at the second step, even if we predict that nobody will select the mathematics exam. We need to have at least one teacher of maths. It's mandatory, because it can happen that someone comes and says, "I want mathematics." Okay? So it's what we call redundancy. We must have a little bit more. And then you can see that we can have 100% of success in prediction. So we can determine the right number of teachers, exactly the right number of teachers, but we accept to have a little bit redundancy. And the level of redundancy is given by the organization of the baccalaureate. So the third step is the prototyping. So the algorithm with the best score, redundancy and accuracy, the good compromise between both of them, is random forest. So it's a kind of algorithm you can find on R or some other open platform. And we did the simulation for the current year. So we try in real situation how it performs. So we take the date, they have been published, the result of the first step. We just select the students we have to pass re-exam, and then we compute the number of teachers with a redundancy level we accept of about 30%. It's relatively high, but lower, than for the previous year. And then we add the new constraints that are related to the baccalaureate. You have to know that each year there are new constraints because there are different situations depending on what really happened, and we have to organize exam center and so on. And these constraints, we know them only 1 week or 10 days before the real exam. So we have to design a very adaptive algorithm to be able to learn with these new constraints at the moment you know these constraints and to readapt. So we need to have very flexible algorithm. And then we have to determine, the new question is how many teachers per exam center and per discipline we need to have. We did that. It has been used in real situation. It was last week, the end of the process, and we have the results for the year. And the national organization is very happy because they have a very strong decrease of the cost of the bag. Just to give you an example of that. The second project is a national project called DUNEOL. It's for the development of experimental university in order to test new processes in all compartments of the university. And I will tell you about learning analytics. So if you remember the Gartner figure here, I will tell you about the DUNE project, and what we need to have in this project is both descriptive analytics and predictive and prescriptive analytics. So it's always the same development process, and we need to have the business understanding. So I will explain you what is the aim of this project. You know, we are within the higher education institution, and staff are encouraged, faculty members are encouraged to undertake further learning and teaching innovation by integrating technologies, video annotation, blog, social file network, LMS, and so on, anything you can imagine. And the prolific use of technology in higher education leads to an unprecedented collection of data in learning. So it's interesting for data miner, but what is also interesting, it's something that have been stated by researchers in educational sciences, is that all these technologies weaken the feedback loop that exists between learners and teachers. When I see my students in a classroom, I am able to see some signs, some impressions, some thing on the figure and so on, that could let me to know if they are interested, if they are totally lost, and so on. And if I take just these two pictures, perhaps you have seen them. The first one is from the 16th centuries, and the right one is much more recent. It's in an amphitheater in the American university. And many pedagogical cues about a student's engagement are easily picked up by instructors in face-to-face settings, but are significantly reduced through online technology. You see the situation is quite the same. On the right side, you have more electronic devices than in the Middle Age, of course, but you have always a teacher in face-to-face situation with his students. And if you are very attentive, very aware of what is on these two pictures, you can see another similarity. If you are a teacher, you can see that in both situations you have a sleeping student. And if you are the teacher at that moment, you can know why the student is sleeping. Perhaps because what you say is too easy or too sophisticated. Perhaps it's a day after a fest or something like that for students. Perhaps it's because it's a student working in order to have a salary and so on. You can know that. But when you are in e-learning situation, you can't have these cues. So how to do? And the learning analytics purpose is just that, to answer this question. Learning analytics is defined as the measurement, collection, analysis, and reporting of data about learner and their context for purpose of understanding and optimizing learning and the environment in which it occurs. It's something relatively new because this definition has been set 7 years ago. Less than 7 years ago, and it was a new discipline at that time. So what is interesting in learning analytics? So it relies on data mining technologies, and also it adds a dimension of prescriptive analytics. So you are able to determine actionable actions to do in order to support the students. So the project, the UNEOL project, is about learning analytics, and we have two objectives. You know, in the French system, perhaps it's the same here in Brazil, we are a public French university, and when you have the bac, the exam just we told about in the previous case study, you are allowed to come to the university for free, and we can say no, it's not possible to come. So we can have a lot of students coming at the first year of the university, and most of them, after a few weeks, have difficulties and drop out. Or even if they don't drop out, we have some other problems of suicide and so on and so on. So the question is, how can we support our students in order to make them successful? And how we have many students in our university. We have combien on a d'étudiants en ce moment? 10 000 en première année? Oui. We have more than 10,000 students, I can't remember, at the first year of the university, and only 1/3 will achieve a license degree. So we have to support our students, and we have also to support students' engagement, how to make them engage into the studies they do. And we have to keep in mind, as they are students, so human beings, we have to avoid side effects such as informational overload. We don't have to give you too much information, because too much information kills information. And we have also to avoid the brick buzzer effects. So when you are a student, you don't want to be sure that someone is watching at you at any moment in order to capture and to store and to analyze data. And the second point, which is important, is the one-size-fits-all principle does not work in education. So we have to be personalized for anything, and also for learning analytics. And so we have the data, perhaps, what kinds of data, what kind of algorithm, and so on. So the first question is about data understanding. So just have a look. It's the data here are about my universities, but I think that they are equivalent to what you have here. We have a lot of IT everywhere at the university. So we have a lot of, we have 15,000 computers, we have more than 8,000 online courses and MOOCs, and so on and so on. So we have a lot of technologies, and these technologies lead to a huge amount of data. Just to give you an example, for all online services, we have 61,000 users per month, and it means that we have 4.5 million of connections per month, and each connection leads to at least 100 or more events, data events, and so on. So we have a very huge collection of data. It's the idea of the project. How can we use all this data to answer the question of supporting the success of students? For the question of data preparation as the data infrastructure, as there is a question this morning at the end of the panel, so we will have a separate discussion about that, and Azim will show you how we do that. About data modeling. The problem of data modeling here is how to determine which kind of student you are, and how we can support you by giving you the right recommendation. I don't know if you know Wally, but Wally is someone very popular in Europe, and if you have children, perhaps it's the same here. You have this question, you have a picture with a lot of people, and then the question, you have a photo of Wally. Wally is this young boy, and the question is, where is Wally on this picture? I just will to give you the answer. Wally is there, and what we have to do is something very similar. We have to find Wally among all of our students, so we have to determine which students needs help at a given time. And then it's exactly the same questions and finding Wally among a very big picture of people, but the task is a little bit more sophisticated because, you know, here you have a picture of all the people here, but in our case, we don't have any picture of anybody. The only thing we have is the data that we can collect on the behavior and the interaction of each people with the system. The second difference is that we don't have a picture of Wally. We don't know who is Wally. We only know some features about Wally and some characteristics. For example, we know that Wally, who is interesting for us, is the students who will be not successful at the end of the semester. So we have to find Wally among thousands and thousands of possible Wallies, but we don't know who he is. We only know at the end of the process how he must be, and we don't have too much information about all the students. We only know the data collected during the interaction with IT technologies. And we have one more sophistication here. This that the difference between someone being Wally and not being Wally is very, very smooth. We have a lot of people looking like Wally, but who are not Wally. Okay? And the data mining algorithm has to find Wally among all the possible Wally without knowing who are the people, who is Wally, and with a lot of people looking like Wally but being not Wally. And the result of that could be different kinds of tools. We can have predictors, indicators, so we can compute a lot of indicators. We can visualize the dashboard, and we can have prescription. So if you remember there, what we will have here, for the first question, what happened, who are the successful students? And then all the others are not successful students. We have to do some action in order to support them. We need to answer the second types of question because we need to know what explains a success. Because if we can determine why a students will be successful, so we can recommend to another one something equivalent. But we can recommend if there is similarity between the students, the successful students, and the students with problem. We have also to answer the third question. And the third question is when we face the students via data, we have to answer the question, will the students be successful at the end of the semester or not? And if it is not a successful student, we must be able to answer the question, what should the student do to be successful? Okay? So we have to answer all the questions. The first one to know who are the students. The second question to answer, how can I explain it's this kind of students? Then how can I predict the end of the semester? And how can I support all the students to be successful? If you remember the algorithms that Azim showed this morning, if you remember, we have transactions, and between these transactions, we can mine patterns, which are the recurrency among the data. We do exactly the same thing. We do that with a session. A session is, I can't have the name of the student, so I only have pseudonymization, so I have a ID 1, and I know the sequence of actions that the student did. And I know that for all the students, and so I have a lot of action. Each time you do something, we have the sequence of actions. And then I can find, with using some improvement of the a priori algorithm we told about this morning, I can determine some rules. For example, if you have the action R13 and R65, I can, with a high probability, predict that you will have R53. But if you remember here, it's only with the students' activities. But I have additional sources of information. I told you. For example, I know, because it's, for example, resources on the Moodle platform, I have the description given by the teacher of what is this resource. So I can know, for example, that 13, is an exercise in mathematics in the field of analyse numérique. And then I can do that for all the elements I have there in order to determine something much more precise, which is the real sequence of action that the user did and recommendation rules in order to know what to do. And I have also additional sources of information. I have the agenda of the students. I have also all the students' activity and so on, Wi-Fi connection and so on and so on. So I can build a very precise overview of what is a student and what he is doing. And with this information, I can learn what is a success path and what is a failure path. I said this morning, we must know what is the question we want to answer. It's something very important because using the same data, we can mine different kinds of knowledge, and some of the knowledge are of no interest. For example, I will give you the example of the how to learn chess, and you know we can have here it's a chess master on the right, and this man is playing with a lot of people the chess in parallel. And then we can collect all the data in order to know how to play, how to be a good player in chess. And then we collect, it's just an example, we collect all the data, we mine the data, and we can determine that a good chess player is someone who plays very quickly. Because the master, here, the chess master, needs no time to think of what he has to do because he's a very high-level player, and the other one are just learn how to play chess. And then, after that, with this rule, we can just take a new player and saying, if I want to help you to win when chess playing, you have to play quickly. It's not true. You know, if you are a chess player. So we must be aware of what we are learning. We don't need to learn evidence, and we must be aware and critical of what we learn with data mining algorithm. It's the reason why I mentioned this morning that we need to have information about the quality of the rules that we mine, of the patterns that we find, of the knowledge that we define. And this measure, you have this morning an explanation about the lift, for example, the confidence and the lift, but we can have very much more sophisticated measure in order to say what I discover, the knowledge I discover here, has no interest. Okay? The last step of the process is the data visualization. After that, I have compute a lot of information about each student, but I have to be able to give to the student an overview of what I have determined about him. So it's the reason why we co-design with teachers and students dashboard. So it's a very generic one. After that, it can be customized and much more pleasant to see. And this dashboard must be available on any device, smartphone, connected watches, and so on. So you can have some declination of it. And then you will have information. And I said before that a one-size-fits-all is not a good solution in the field of learning analytics, not only in learning analytics, in many applications. And then I have to let the learner decide of what kind of information is useful for him. So he have a lot of measure, and he can select which one he thinks are nice, are informative for him. And after that, in the second part, here, sorry, it's written in French, but it's really, except the design of the tool, is exactly what we propose to our students at the next academic year. And then after that, we have tips. We determine rules. We know that we can improve the success support. And then we can give tips. And then here in this left side part of the picture, you have tips. And tips are personalized. So we say, okay, it's nice, you have a a great job for the mathematics and so on and so on. Or we just suggest that perhaps you need to read again an open educational resource on the topic of physics because it's not so evident that you have all the bases and so on. On the left part of the dashboard is all the personalized information which answer to the questions. The first question of the Gartner figure, say descriptive analytics. On the right part of the dashboard, it's all the information answering the prescriptive and predictive question of the Gartner figure. The first one here is how I am relatively to my peers. There are a lot of results in educational sciences showing that if you compare yourself with the performance of others, it's like in sport, you will be better. So here you have the dynamic trajectory of a specific learner, and you can see relatively to the others, the best ones, the worst ones, median, and so on, and how you are. It's the third question is answered here by the last here on the right, is my future. So as a student, if I go on working as I worked in the past, what will be all the possible future I can have? We can only say you will be successful or you will not be successful because it's something very hard to read when you are students. But we can give you an idea of all the possible future you can have, and for each future you can have additional information and you can have the probability it will be yours. So it's that about the project. The project Junior. This will be tested with our students at the first year at the entrance of the university. The third project I will mention is something similar, but with different data, so different algorithm and different context. It's a learning analytics, but at the secondary level for learners about 11, 12 years old, you know, at the beginning of the secondary. And this project will be presented by Azim, because it's your... It will be... Oh, okay. Just... Oops. And here we will describe the data infrastructure, because this one is more interesting than the previous one. If I just have to mention what are the differences with the previous case, is that when we speak about students, we have a very big population of students. But when we have the pupils with 12 years or 13 years old, we only have 20-25 pupils by learners by classroom. So we have a very small amount of pupils. We have everywhere in France, but in each classroom only a small amount of them. And we can use the same algorithms, because the algorithm we previously used require to have a lot of, to have big data. And here we don't have for each case big data, only a small, it's a small data example. So,
thank you, Anne. So this morning in my talk, I postponed the presentation of the metal project because it's the same topic than Anne presented previously. So this is related to the Anne presentation and my presentation of this morning. So let's go back to the data selection issue in metal project now. So as Anne said, metal project is similar to EOL project presented by Anne, but the population is the secondary school. So we tend to develop these learning analytic tools for secondary school in France. So one of the tasks of this project that I have in charge is collecting data to an LRS. So LRS means Learning Record Store. So we have a place where to store all the data we intended to use later for learning analytics application. So why collecting data? In our case, it's in order to design new online personalized and adaptive services. It's the ADN of our team. Our team investigation area is to model predictive behavior of the user. And these models are based on digital footprint. So it's exactly what we want on this project. So data are our raw material to work and to test our algorithm. There are constraints to do that. There are two kinds of constraints: technological, it's obviously, but also regulatory and privacy. So that's led us to define some good practice, some principle to observe to collect this data. So minimization of collected data means that do not collect useless information. It's mandatory in the new regulation in Europe. The transparency means that provide information about what you collect. Explanation, so prepare data for explanation of choices, service recommendation. Right of oblivion means that we must enable the right to be forgotten. Informed consent means that you have to identify data that are covered by the user consent. And the last one is to store data secure. We have to store data in a secure technological system. So to comply with this principle allows to go to something that we called privacy by design. So we have to design the thing, the privacy issue at the beginning of the project. So this is the process we use. It's a very classical process. The business understanding at first step, data understanding at second step, data modeling in third step. There are something particular in this project. We studied standard, and then we defined connector to feed the learning record store. Let's take the first. What are the issue? What are the question about the first step? Business understanding. The question are who are the stakeholder. So it's not an easy thing when you work on this kind of ecosystem to identify who is who, and what are their roles. Do they own the data? Are they external provider? Are they just partner? What are the status of IT services? Could they give this information? All of these questions are prepared in the business understanding. The next step is the data understanding. Data understanding has also question. What are the useful data? What are their availability? It's in real time or not? Do they use standard? What are the status about the GDPR? Are they legal? Can the IT service provide this information? So this schema summarizes our understanding of data. So we have four in orange color. There are four stakeholders: internet provider, a local IT service, personal virtual desk, and learning management system. All of these stakeholders have application like proxy. Proxy give information about the log of the users of services at a high level. Local IT service provide a directory which is connected to the user database. The virtual desk propose many services, so you can plug many services in the personal. You can extend your personal virtual desk with services, and these services work with the database about academic life database. And the last one is a learning management system. Learning management system contain various kind of resources, educational resources. So teacher and student and pupils use these resources to learn. So there are two kinds of resources. Some of the resources are standardized, so they give directly standard information. Here we use XAPI. So the result is XAPI statements, or sometimes just log in raw text. So it depends on resources. So the next step is how to model data. So the questions are how to represent them and how to band them each other. So as you know, this is multi-sources data, so they need to be bound. This is this diagram. It's an UML diagram. It's that represents the conceptual model of the data. It's a simplified diagram, but that give all the principal information that we can collect from this organization and that we can use for our own application. So you find here the users, the courses, the statements, and so on. So this schema summarizes the last version of of the conceptual model of the data. And then we studied the existing standard and we selected the one that seemed interesting for our approach. So we have selected one roster which is used for educational descriptive information. One roster was formally designed for American educational organization. It was designed for interoperability of educational databases. So we just use this standard to import data from databases. So we needed to adapt this standard to the French organization because American law is more permissive than European law. So we have to reorganize something like ethnic group or religion is forbidden in France. You can not record that in a database or in a file. So one roster was redesigned, readapted, but the basis is the same. We use also SCORM. SCORM is a standard that's very common for describing educational resources stored in the learning management system of each organization. Then the last one is XAPI. It's a quite new standard, but it's very interesting because it's designed for the storage of learning usage data. So the main advantage is that we keep data in the raw format. So this is an example of XAPI statement. So what you see here, it is based on the notion of statement. A statement is composed by verb, subject, object, and some contextual information like timestamp. So in purple, you have the verb that could be used for the XAPI. So here, the subject is Pierre for the first and Jean for the second one. And the object is the educational resources, exercise number 1, exercise number 2. So in the first one, we could read that Pierre have completed the exercise number 1 and exercise number 2. He has read the document which called the system d'équation, equation system, and he abandoned the third exercise about linear equation. So you can describe just with the statement, with the raw statement into your learning record store with XAPI, with statements that are described like this. So XAPI is used for feeding permanently the learning record system. So the idea is to move toward data lake and not only repository, simple repository. So the new concept of data lake is we can define data lake as a storage repository that holds the vast amount of raw data in its native format, including structured and semi-structured and unstructured data. So we have no constraints about data. The data structure and requirement are defined until the data is made. So you just store the data in the first step, and when you want to use, you just extract this data from the data lake. So this is a new concept, and there are more and more papers with this concept of data lake, which is more than repository used in data mining system. So I finished this example, so we can switch, and it's your turn to for the next recommender system.
Do you want to break just now, a few minutes of break? I don't know. What's plan?
Olá, pessoal. Alguma pergunta? Ou deixar para o final? Continuar, então?
No? Okay. Because I forgot to ask this morning. I was told that. So the fourth panel is about social recommender systems. Just remember, I told you this morning the example of how to go to the cinema tonight, and then to have a good recommendation in order to know how to have a good evening. So just let you remember that a recommender system is the principle is the following. You have a lot of items, a huge number of items, and you have a user who wants to know which items are relevant for him. And the aim of a recommender system is to determine among all the items the subset of relevant items for a given user. So here we have to understand user needs. For that we will use usage data. So all the things that you do, and then we will mine the data in order to answer the question, the third question, prediction. So the assumption of a recommender system in social recommender system is a user with similar taste in the past will have similar taste in the future. So if you like same movies than I liked, we can imagine that you will like the same movies that I will like, and something like that. And we will use to do this social recommendation the preference of a group of people to determine what is relevant for a specific user. And I showed you this morning, I love this movie, and then I asked people on the web who loves the same movies and I love, and then we determine the community of what is called similar users with the same taste, and then we will look among this community what are the other items they like, and then we will recommend the best one to you. And this technique is called collaborative filtering. It's a very famous one. It has been used on many platforms. For in e-commerce, for example, you have collaborative filtering on the Amazon and some like that. It's a specific collaborative filtering. And the principle of the algorithm will be the following. We collect data. We collect usage data. So what are the usage data we can have? The second aspect, we need to determine who are the members of your community. And your community is all the users with the same taste than you have. So it's what we call similar user. So the second question is, how can we compute similarity between users? And the third one, when we have determined your community, your specific community, how can we use the data we have about this community in order to compute predictions for you? So we have 3 questions to answer. What are the data? How can we compute similarity between 2 users? And then how can we use the similar user in order to compute predictions of the items to recommend? So we need for this social recommendation to have a large group of people. If you don't have enough people, it will not work. You must have a minimum of people in order that it works. Because we need to find people with similar tastes. And if we want to find people similar to you, we must have enough a broad panel, in order to be sure that we can find people with a high similarity with you. So the input, the first question is, what is the input of that, or what are the data? But just before that, you have to remember, perhaps you heard about that, it's a Netflix competition. In Netflix, I think that you know it's a video on demand service available on the net. And a few years ago, Netflix launched a competition about how to recommend to users of the Netflix service items movies to look at, and they have an algorithm running on the Netflix platform, and they ask as a criterion of success of a 10% improvement of the quality of recommendations. So the winner will be the algorithm able to have 10% of improvement of the accuracy of the performance of the algorithm used at the moment by Netflix. And the prize was interesting. This was $1 million. The competition is close. Some researchers win that. And the only data, all of the researchers have exactly the same data. And the data are only a user ID, the movie, the ID movie, the user has selected, the time it's time stamped, and the rating the user gave to this item. Only that, you know? And the question is what to recommend. So we have 2 different families of techniques to answer this question. Mainly, if we speak about collaborative filtering, we can categorize them by memory or model-based. Memory-based system, it's just to use all the users in real time and to determine who are the most similar user by computing a similarity. Only that. It's a principle of what is called the K-nearest neighbors. It's a very famous algorithm, perhaps you know about him. And you can use it either using user to determine which user could be interested for a specific movie, or you can use it in order to determine which movies are the most relevant for a given user. You can have both aspects. The second family of algorithm is what is called model-based collaborative filtering. The idea is if you need all the times to compute all the similarities for all the user each time you have to compute a recommendation, it will be very time consuming. So perhaps we can pre-compute something before, which is called a model, and this model will be learned on all the data you have, and when you have a specific recommendation to do, you run your model, but you don't have any more computation, too much computation to do. The advantage of the model base is to be more real-time than the memory base, but you have a problem. You have a drawback with this kind of algorithm is that you compute your model once time offline, and then when new data arrive, your model is not able to learn on time all the new improvements, and then you can compute recommendations that are not so good and so performant. Then you have to retrain regularly your algorithm or to find a way to do that. So I will explain you first the nearest neighbors algorithm. I don't know if you know that. I try not to use too much formula, but just to explain how it runs, and you will have the formula on my slides, and if you need it, you can run it. It's not so complicated. So just imagine you are Joy, and as a fan of movies, you have seen 3 movies, and for each of these movies, you have had a rating, your rating on this movie. And then the second step is that you can find all the users within the Netflix community who have seen the same movies with the same rating or similar rating. And then here you can find 3 of them. For all these 3 users, you look at what they have seen. You have here with on the right row, you have all the movies they've seen, and you can just say the movies that all of them have seen should be the best recommendation for the specific user you have, Joy, here. It's a principle. It's very easy. So, just before, you have to know what are your data. What do you have? Just remember, you have an ID for the user, you have an ID for the movie. Here I write just a name, but you have only an ID. And if the user, for example, Lisa, saw the movie Lady, you have the rating that Lisa gave to the movie. So here she says on the Likert scale, from 1 to 5, she says that her rating is 2.5. And then if you look at a line of this matrix, you have what we call the profile of a user. And if you look on the column, you have what we call the profile of a resource. It's okay? And you have only this data. Here, when you look on this example, you have only a few users and a few movies and just a lot of ratings. But the situation is that you have millions of users, thousands and thousands and thousands of movies, and that, of course, all the users do not spend all their time looking at movies. So you have only a few ratings, and just we have what we call a sparsity problem. You have only 4 or 5% of the matrix with rating. So we say that we have 95% of missing data. At least. On some Netflix databases or other databases, it could be 98% of missing data. So only very little information everywhere. It's only the data that you have if you want to compute recommendation with that is a collaborative filtering. So you can have the ratings when you have good users saying, oh yes, I will write my rating on the movie. But most of the time you take the recommendation, you go to the cinema, you look at the movie or at the video on demand, and you never come back to the website and you never had your rating. So if anything is okay, we have at a maximum 5% of ratings. But most of the times people do not rate. So we first have to give an estimation of what should be the rating given by a specific user on a specific movie if he has rated. Only knowing the data that we can have, it's the time he spent looking at the synopsis of the film, the actors on the film, and all this kind of information. So we can have either explicit ratings, the user rate, or we can have implicit data. Using all the usage data that we can have, we can compute an estimation of what should be the ratings that your user writes if he had the rating. And here you have a formula here showing how you can compute this rating depending on the kind of data you have and on the weight and the importance of each data. The second question, knowing this matrix of information, is to determine what are similarities between two users. And the first question, how can we determine how similar people are in their taste? So we need what we call similarity measure. You can have plenty of similarity measure, and one of the most popular is the Pearson correlation, that I'm sure you know this correlation. You have here the formula in case of you don't remember. And then you can have just a correlation which is like a similarity between two users. You can use the cosine measure, you can use any kind of measure, but this one works very well, so it's the reason why I mentioned this one. So you are able to compute the similarity between two users. Of course, you use only the co-voted resources, and you will now make predictions. So the third step is to say, I will keep only the K more similar user to a given user. And K is a parameter feature of the algorithm. And then I will compute using the information about this K user, the prediction of rating of the rating of the movie for the specific user I want to recommend something. I'm not sure I am very, very clear there, so I will try again. You know you have determined similar user, K similar user. For each of these user, you know the ratings he has put to movies. And now for given movies that the current user never saw, you want to estimate how we should like this movie or not in order to know if you can recommend this movie or not to him. And to do that, you will use the rating that the user of the community have put on this movie, and you use as a weight of this rating the similarity between the current user and the specific user you want to recommend something. I don't know, it's clearer? Yeah? It's okay? And since you have this formula, you see that we use a deviation in order to take into account if you are a pessimist or an optimist when you rate. Because you have users who put only 4 and 5 ratings. 4 it's I dislike this movie, 5 is I like this movie. You have others who do the same with 1 and 2. So if you remember, here is the data I have. With this kind of measure we have, we can compute here the similarity, so it has been done with the formula I give you, and then determine which movie I can recommend to you. So if you look, it's for Toby. I just, for Toby, it's the last one. I will compute what should be the rating of Toby for the movie Lady, for the movie Luck, and for the movie Night, if I have similar people liking this movie. And so I did the job here, and we know who are the movie you can recommend. It's okay or not? Yeah, it's okay. So it's a collaborative filtering. It's the most popular way to do recommendation, social recommendation, and it's broadly used in many applications. Most of the recommendations you have now are based on this collaborative filtering principle, sometimes with an hybridation with content-based, that you use the metadata you have about the movie in order to reinforce your recommendation. If I note that you give always high ratings to romance, if I find a romance in the prediction with a high ranking, I will select this one before any other. So it's what we call content-boosted collaborative filtering. But it's the principle of the algorithm which wins Netflix competition. But if I have all the Netflix users, it is not easy to compute that. It takes too long time. So you can use what is called matrix factorization. The main idea is to determine latent factors of user, for example, and to use them in order to predict ratings. And one of the most popular latent factors determination is the singular value decomposition. If you are interested, you have all the theory here, and you know that what you aim at doing is to reduce the size of the space. You know the matrix is very big, and all this information is not synthesized. So what we try to do is to determine another space, a latent space, and then it's a space with a smaller size. And then you can have what is called matrix factorization, so you have the decomposition. You can read that. So it's this algorithm with matrix factorization who wins the Netflix competition. And now you have a lot of improvement of this algorithm, but you will know that how we can assess the performance of a recommender system. One of the most, I don't know what I have here. I'm sorry, I think it's not very easy to read the formula. But here we have what is called the mean absolute error. If you read papers or if you read documentation about algorithm, it's a measure that is most of the time indicated because it's easy to compute, it's easy to understand. The example is you have a set of a data set to train your algorithm, to learn your model, matrix factorization model, for example, and then you will use 80% of the data set as usual in order to train your model, as a 20 remaining % in order to assess your model. And then using the model you have designed, you compute the prediction of the model, and then you compare with the 20% of results that you have, and you compute the difference between what you have computed and what is the reality in your databases when the information is available. And it's what is called the mean absolute error. So an MAA of 0.7 means that the algorithm on average was off by 0.7 stars. So it's very easy to read the results and very interesting. One of the other measures very popular on the recommendation system is the root mean square error, RMSE. We amplify the larger absolute errors in order to say when it's very similar, it's not important, but when the deviation between the computed value and the real value is very high, we have to amplify that there is an error, so it's the reason why you have a square. So it's the only difference. It's the one which is the most popular and used in the Netflix algorithm, and it's the one that with this 10% of better accuracy using the RMSE, which wins the competition. But at the same time, if you remember, the winner is the one with the 10% of improvement of the accuracy compared with the previous algorithm used by Netflix. But at the same time, some researchers want to determine what the user really perceived from a recommender system. It's just the year the winner achieves the objective of the 10% of improvement. Researchers show that 10% of improvement are not perceived by a user. if I give you a recommender with the previous Netflix recommender and the one with the matrix factorization with 10% of improvement, you don't detect any difference. It's exactly the same perception by the final user. So Netflix has lost $1 million in order to improve its algorithm because it's not perceived by user. But it's not that which is interesting. Which is interesting, say why it is not perceived by a user. Because accuracy is not the only human factor that a user can perceive. He wants accuracy, of course. If you say go to see this movie and he hates this movie, you have no chance to be used. But it's not the only thing you have to know. You have to take into account a lot of human factors that have been studied. And here you can see that precision, so accuracy, is one of the factors. But for example, the diversity also is something very important. And among the process of recommendation, you have different needs of diversity. Just for example, it's a work that has been done in France and in China in order to compare how recommender systems were perceived by final customers. And it's just a website in order to buy perfumes. You know, it's a very interesting topic for recommender system, and because when you buy a perfume, you have to smell it. But when you buy it online, it's difficult to smell it. So you have to use different kinds of feature in order to perceive the customer, to convince the customer to buy your perfume. So it's an interesting case for this kind of work. And then what is stated is that when you are in France, at the beginning, people want to have a broad choice of perfumes, all the catalogs. After one or two interactions with the system, they want to have a very small amount of perfumes and then to do the selection. When you are in China, it's something quite different. They want only, not all the catalog at the beginning, they want to have some perfumes extract randomly or not from the database. After that, after a few interactions, they want to have only, as the French people, a very small amount of perfumes to do the selection. But they want to go on with the interaction with the system to be convinced that this selection is the right one. And so they want to have a broader set of recommendations in order to be sure that the choice they will do is the right one. So you have different behavior, depending on the final user and depending on the culture and so on. So you have to take into account in the way you design your algorithm these kinds of human factors, and then here you have a panorama of the different you can have. You can have diversity, personality, depending on who you are. You can have memory, if you can remember a long sequence of recommendation, or if you want to have just the answer just at the moment you decide to buy something, serendipity, novelty, and so on and so on. So when you design this kind of algorithm, accuracy, performances is something sure very important, but it's not the only thing that you have to take into account. And when you write the code of your program, you have to take into account this kind of information, and you also have to learn that by the data you have collected. So you have a lot of scientific challenges such as accuracy, the problem of data sparsity, because 99% of missing data is something very hard when you train your model. But you have also some specific problem related to recommender system. The two first are common with any data mining techniques. You have the cold start problem. When a new user you comes and want to use, for example, Netflix. Netflix does know anything about him. How can the system recommend something? And when the recommendation at the beginning, it can only say what are the most popular items and things like that. But at which time is it possible for the algorithm to do a recommendation and to be sure that the recommendation is good, because the user will have this one and he will have an opinion about the site based on this personalization. So you have to develop specific algorithm in order to be able to give you, at the shortest as possible, information, recommendation, but also the confidence, the quality of the recommendation. Not only recommendation, but associated with this recommendation, the quality, the estimated quality of the recommendation, the confidence you can have. It's a very difficult problem, because all the algorithm, if they give you this recommendation, is because they think it's the best one. So how to determine what means best for a kind of algorithm. You have the gray sheep users. I mentioned that. Most of the recommender systems have been designed to be able to fit the expectation of 50-55% of the population. Not all the people. 50-55% of the population, Google say, for the search engine, when we can match the expectation of 50% of the user, we are very happy. But the problem is that you don't have 55% of users, you have 100% of those users. And what happens for the 45 other users? For some of them, you have the cold start problem. Of course, you don't know who they are, it's not a problem. But you have some others. The problem, if you use collaborative filtering, is that you have to find similar users. And similar users sometimes do not exist for a given user, because he's too specific. He's very coherent in his behavior, but nobody has the same behavior. So you can compute similarity. And that is the problem. It's what is called gray sheep user. And now you have techniques able to detect that a user is a gray sheep user, and then to adapt the recommendation process to this kind of user. But you have also another category of people, two other categories of people. Another one is people that want to bypass the recommendation system. They know that you will do personalized recommendation, and if you do personalized recommendation, it means that you collect data, that you will have information about him and the behaviors they have, and they don't want that. So they develop bypass strategy, and these bypass strategy are very difficult to identify, but you have to do that, because if you are able to detect this kind of user, you can disconnect the recommendation process and then offer what they want to have, no personalization. And you have a third kind of user. You have the black chip users. You have the user, perhaps you read that a few years ago, Amazon has said that they do attacks in order to promote some of their products. And of course, in order to convince you to buy some of the products, they must explain the decision, and the way to explain the decision is to show you your community of users and the reviews they report on the products. And so they design virtual user, able to have exactly the same behavior as yours, plus they like this product. Is a kind of attacks and of way to do that. You also have to be able to detect that. There is a need of diversity. And what is diversity? Diversity is just something different from similarity. Similarity is how to have the most similar taste. Diversity is how to provide you with as various as possible items. You have here a measure here on the top of the slides, and one of the challenge of algorithm now is how can we do a compromise, a good balance between the need of accuracy, so to have exactly, to give you exactly what I am sure you will like, and diversity, to suggest you new items that should interest you, because if I succeed in doing that, you will buy more, you will buy things that you never think you will buy, and so on and so on. So there is a very strong question here, how to do a good compromise between these two information. And you have a lot of other challenges. For example, we use ratings, but what means to rate a movie, or to rate a book, or to rate something? With the same meaning, with the same rating, you can have a great diversity of appreciation of users. And when you mind also the review, people write text and you can use the tags or the reports, the reviews they had. It's the same thing. Sometimes when you are nervous for anything else, you put a rating, it is a very bad rating. But even if you like the movie or the book. And sometimes you are very optimistic because it's a sunny day, you are in Brazil, and you are very happy. So you write a very positive review on the book you read, just because the context is pleasant. The book is not very interesting, but not so bad. So you are very optimistic. How can we know that when we use your rating in data mining? And when I put 1 and then after that I put 2, there is a difference of 1 because my 2 ratings. Is it the same meaning when I put 5 and I put 4? 1 of difference. We know that no, it's totally different. And it depends of the user. So you have to learn also about the user, how he rates and what are the influence factors for him. And if I put 5 on my on a movie, and the day after I see a movie much more interesting than the previous one, what can I do? Because 5 is the highest rating I can have. How can I do that? And when I was, you certainly read this story. You know my TiVo thinks I am gay. No, you know this story. It's TiVo is a recommender system available a few years ago on American TV, and then you can have recommendation in order to select what channel you will have tonight at the best to look at. And a boy wants to buy a new TV. He's very happy and he invites his girlfriend. She comes at home and they look at the TV, very happy, and say, please select what you want to see tonight. And so she selects a romance. The day after, also a romance. She stays a few days after she comes back home. And all the day, he has only recommendation about gay shops, gay channels, and so on. Because the interpretation of the TiVo, the recommender system, is that he always look fashion movies and romance and so on. So he must be gay, you know. And how can we know that it is only someone else? That it's called noise in data mining. Additional data that you don't have to take into account. It's not so easy to determine what noise is and to skip away from the databases. And you have to do that. And you have many and many things to think about like that. And what is better, to ask the user to rate a movie or to compare to movie? This one, is it better than the previous one you see or not? And so on. And if you ask the same user for the same movies 2 weeks after, will he give you the same answer? Sometimes yes, most of the time no. So you have a lot of study in order to determine what has the impact of the ratings and how you can use it. And so it means that a rating is a low value data. It's the only data you have, but it's a low data value. I will just give you an example of a recommender system because we spoke yesterday. Ricardo and Tezas gave the example of open educational resources that you have developed in your university and that you plan to develop for the future. And just I want to show you that a recommender system can be used for open educational resources. We designed one in my research team, and if you are interested, you can use it. It's an open software, open license. You just have to ask Azim, he will give you the link for the code. You know, in France we have what what is called French digital thematic universities. French digital thematic universities, there are 7 at the moment in France. It's a kind of national repository of open educational resources in a discipline. So you have more than 40,000 open educational resources available freely, all produced by teachers from higher education institutions, all scientifically, pedagogically, and technically labeled by independent experts. They are all indexed using the French declination of the LOM standard, as they are, of course, all Creative Commons licensed. It means that you can use it when you want, wherever you are, and no problem for any action. Just to give you an example, oops, sorry. So we have here, you have a collection of serious games. Here, it's a case study. It's a case. It's a series of case study. So you are students, and you have to solve an enigma. And this enigma are always taken from real situation. Here, the situation is when the director of company came into a production plant. He has an accident because he received a piece of metal and it was very hard injured. So there is an inquiry and you are in charge of this inquiry. So you have a lot of virtual tools in order to do the analysis you want to do, and you have to find the solution, and you have additional material if you want to have. It's a kind of open educational resources we have. We have another kind of educational resources. It's to learn physics. It's in order to make that students can make at home with everyday life objects, experiments that they did on very sophisticated machine during their curriculum. And then here you can have a lot of explanation how to do things, what you can think, what is the theory behind, how you can realize it at home. Another kind of open educational resources, Here in anatomy, so you have it's how to learn how your body is made with bones and nerves and so on. And then you have a lot of educational resources about this topic. I will just show you. You know, it's a very famous way to teach. Here you see. This kind of resource. You have all the body make like that. It's a way to learn anatomy. It's very old. It has been designed 1 century ago. But when you want to do that, when you are in an amphitheater, you have to take paper, things like that to cut and so on. It's very hard to explain. So here you have all the virtual elements in order to use very small sequences, and you have all the body explained with this method. And then after that, you can combine in order, for example, to show here how to walk or to train students on how to monitor blood depressions and so on. So it's freely available. If you are interested in you can use, of course. But the question is the following. All these open educational resources are available on the website. You can go to the website. You can find the right resource by using a research engine, then take it and use it. But most of the time, when the user comes to this, you have an example here of the portal of the website here on the left. When the user comes to this portal, they don't know how to formulate the request in order to find the right open educational resources, and they left the website before finding what they need. But it exists, so it's a pity. And the characterization of the resources, open educational resources, they are very well described because they have been all indexed, so all very well described with controlled vocabulary. So you have the metadata, you have a very precise knowledge about each resources. But when a user came, you don't know who he is. There is no logins, no passwords, nothing like that. And when he comes again, you have no possibility to know that it is the same user. So you are always totally unknown. But here, on the right part, you have our Moodle platform in our university, and there is the situation is just at the opposite. You have very well described user because they are students of the university, so they are registered in the information system of the university. So we have all the information that you can imagine about each student. But on the Moodle platform, you have resources, as in these resources have absolutely no description, no metadata, because none of our teachers, and I am one of these teachers, had any metadata. So we have two different situations. One, very well described resources, no information about user, and on the other hand, you have very well described users and no information about the resource. But what we know is that the users, the students using the Moodle platform, sometimes they need to have open educational resources because they can't understand what the teachers explain. So they need other way to learn the same thing. And most of the time, the teacher says we don't have any time to look for these open educational resources on the portal, so it's a problem. So the aim of the Pericles software is to do recommendation within the Moodle platform of open educational resources which are pertinent for a student at a given moment. So it runs using only the data available, indexing of the open educational resources, usage data and information, knowledge about the student, the learner, and then it's recommend in your own space, open educational resources saying this one should be very interesting for you at the moment. Okay? If you want to use it, it's totally free. You just have to install it. So it's just to say that you can have recommender system in any kinds of application. I do not mention that we have created a startup about recommender system more than 10 years ago using our algorithm that we developed before, and that most of them are used now in the health context because they are used in order to support the decision of professional of health. It's time now to just see what we can do with this additional kind of data I mentioned this morning, that are this data you can have from social network analysis. So it's the end of my talk. Thank you very much for your attention now and this morning. And now is Hazem, it's you. The floor is for you.
Yeah, thank you. So if you have some question for Anne during my installation, don't hesitate. As you like. It's as you like. So just.
Só para os estudantes, por favor, façam perguntas, porque é uma oportunidade única da gente ter pessoas com esse conhecimento. Então não se sintam-se ameaçados. Gente como a gente faz perguntas. É bom fazer perguntas. Não tem pergunta errada. Tem a pergunta errada é não fazer pergunta. Well, I'm going to do this in English because I think it goes easier, so you don't need a translation for that. I think you can do that. Well, you have been mentioning about the movies as an example, and also again the selection of wine and so on and so forth. But what about our needs? How difficult it is to adapt to your knowledge in everything that you are doing, the way that you are data mining and so on, with the kind of stuff that we are looking for here that is about health. So the number of the variables perhaps is far more extensive or even more complex, I don't know. But I know that is perhaps slightly more difficult than to choose a movie or a song. So what do you think about that, and how can you adapt yourself for this kind of need?
I choose the example of a movie because it's a very famous one, and also we don't have too much privacy consent and so on. But in health domain, there are a lot of in France perhaps. I guess it's the same situation here. We have a lot of rules, and in particular, we are not allowed to do recommendation to someone. The only one who has the right to do that is the doctor or the medicine. But we use that in order to support the decision of the practitioner. Just to give you an example, is for kidney diseases, and you have dialysis. Dialysis, and I'm not sure of the medical term, sorry for that. But the question is that you have to go to a center regularly, and then to spend a day, it's something very difficult, and then you have water taken out of your body and so on. But it's something that does not allow you to have an easy way to live and to have a job and so on. So there is an alternative. You use peritoine, you use a membrane, you have something here, you don't know, yes, and then you can use it with some solution here, and so the dialysis is an ongoing process. But the problem with that is you have to determine the pH of the solution at any moment, and you can have also problem here. And then you can have a system. It's working in France. It has been developed in my previous team. It's a system that collects the data that the patient can give every day. So it's blood pressure automatically measure, the temperature, and so on and so on. And with this data, it's a lot of personal data you have. Data mining algorithm works, and then say, oh, it's time now to go to the doctor because now you will have a problem. It could be an emergency. And then there is an alert to the patient. And there is also information given to the practitioner, to the surgeon, not the surgeon, to the physician, in order to say, just look that. And if it goes on, the prediction will be that. So you will have time now to do something, to give action. So there are some kinds of things like that. There are a lot of other data mining applications in the field of health. For example, to determine what could be the side effects of medicine before the creation of this medicine. Because you have a lot of data about the side effects of all the medicaments. You know how each medicament is made, and then you can compute predictions about what should be the side effects and so on.
Just to carry on with the same question, I can believe that the professor here has more or less the same idea when you are talking today in the morning about outbreaks or something like that. If you're talking about syphilis, for example, and then you have like what is going on in a network, and I believe that tomorrow we're going to talk with DataSUS, that's our system here in Brazil that controls the health system as a whole. And this is the kind of thing that the example that you gave is like very specific. We're talking about kidneys and dialysis and all this. What I believe that we are talking about is when you see the whole country and what is going on in very specific populations and some poor areas and areas that are not well assisted or things like that can spark something. And it's very casual. It's here, it's there, and eventually you have, I don't know, you have the variables. Question is, can we adapt your knowledge, everything that in this sort of a situation? Or do we need to adapt something else? What's the challenge for that?
To the best of my knowledge, the answer is I never saw that at the moment because you have a lot of sources of data, huge amount of data, and so on. But what we describe today is only a kind of algorithm in data mining, how to find patterns, regularity in things. But what is interesting, if I understood your question this morning, is not to determine the regularity, but abnormality in some sometimes, just something appearing, and that could be very interesting. And there is a kind of algorithm able to do that in order to say, oh, we work on this kind of algorithm. If you want, I can send you some information about that. But we are able to determine that anything seems correct, but here there is something that could make us predict that something will happen in the future. And if we have this event at this moment on this kind of people, we have to be aware of what could happen and so on. And if this other event occurs, then we could know that something is wrong and so on. So it's another kind of algorithm. We work not only by similarity, but also by dissimilarity. So, for example, it's very interesting to know that you have the same behavior at the movie, I will take this example again, than me, because we have similar tests. But perhaps it's more interesting to know that we are exactly the same. We have exactly the same taste, except for this movie and this one and this one. Because if we can model the system just doing that, we are able to detect the difference. And when we know the difference, we can analyze them and then run another kind of algorithm in order to determine which one are relevant, which one are not. But it's still a research area. It's not... Yes?
Professor, sorry about that. Okay, so take your time doing. Well, the next one is about the stress test of all the algorithms. So when you have really good amount of data on that, is there any limitation that you should be aware of when, that it can take time and it costs a lot? So you are just processing what increased infrastructure, what perhaps platforms are not good enough to do this kind of stuff. So what are the limitations on the algorithms and all the math on that?
We still have limitations, and we'll still have to develop alternatives. We can do parallelization, of course. We have NoSQL database and so on and so on. But we are able to give an estimation of what is possible and what will require more additional computers, additional memory, and so on and so on. And sometimes you have a scale effect. Still given amount of data, it's the same cost. And then you have one data more, and that it's exponentially increase. Right?